Let's continue our discussion. Yesterday we talked about Kafka. We understood what a Kafka is, and we understood some of the concepts of Kafka like producer, consumer, topic, right? And little bit of partitions. Okay. Now today we'll try to understand this Kafka architecture, which means I want you to understand how exactly all this things works in parallel inside, right? So we say, okay, I have written some data to a Kafka. We say, hey, I've consumed some data from the Kafka, but let us go one more step ahead. Okay, so we'll start with the diagram. Okay, so let's say this is your Kafka server. I'll say this is your Kafka cluster. This is your Kafka cluster. And Kafka cluster is nothing but a combination of more than one broker, is not it? And broker means typically a system, a machine. So let's say this is your machine and this is your another machine, right? So I have node 1, I have node 2. Okay, and in these nodes, what we have done is we have installed Kafka. We'll learn how to install Kafka later. Okay, so we have node 1, we have node 2, and in this node we have installed Kafka systems, right? And they are all up and running. Okay, now this is called as your Kafka cluster, and what you would do now is you would start producing the message, right? So you'll have a producer. Okay, you'll have a producer 1. You have a producer 2, you'll have a producer 3, something like this. Okay, and these producers are typically some sort of program. Okay, usually it would be a Java program or a Scala program or anything else. It would be a client, right? We will learn how to write our own producer maybe in the coming session, of course. Okay, then these producers would start writing the data to a Kafka cluster. Okay, now in order to write the data, what producers needs is the IP address or the name of broker. IP address or the name of a broker. See, when I say broker, I'm talking about these servers, right? You know that these servers are called as broker. Okay, so this is your Kafka server, this is your Kafka server, and each of the server have a IP address. They run on some defined ports. Is not it? Now, Kafka has an automatic concept of what auto discovery. Okay. Now, in a typical real-time world, you may see hundreds of Kafka cluster, like hundreds of Kafka nodes in a given cluster, which means one cluster may have many nodes put together. It depends on how big your organization is, how big your data is streaming. Okay, so for our understanding, let us say we have a Kafka cluster of just 2 nodes, right? And let me give some IP address to this. It's say 192.23.24.1. okay, and let me give some IP address to it, 192.23.24.2. okay. Now whenever this Kafka cluster is set up, whenever the Kafka cluster is set up, after this is done, the producer need not connect to all these machines. Okay, so whenever you're writing a producer code, all you need is one IP address. That's it. One IP address of any of the servers. Okay, and we also call the servers as bootstrap server. We also call these servers as bootstrap server, right? So whenever you are writing a producer code, right, so you need to have a connectivity between your code, your client code, and your Kafka cluster, Kafka system, right? And all you need is one single IP address. And if you are giving only the IP address of the first node, that's it, that's done. Okay, and automatically whenever you are writing the data, okay, your Kafka has a feature called auto discovery, which can help to get the information about the other servers. You really don't have to specify all the server details here. You just give any server ID, and internally, right, Kafka has a mechanism to auto discover the other servers. Okay, so that would be taken care by the framework itself. As a programmer, you don't have to do anything on it. Done. So Now the producers are here, and then what we'll do is whenever you want to write a message, you will write a message in a topic. It's not it. So you will create a topic. Okay, we will learn that. Don't worry. You'll create a topic in server. So the topics are created here, not here. The topics are created here. Okay, and it is also possible to auto create the topic, which means whenever I write a producer code, I may say, hey, I want to write this particular message in a topic called SMS. Okay, and if you do that, if SMS does not exist, then there is a technique of auto creating the topic. Okay, so we'll talk about that practically in the sessions. So you will create a topic in the server, done, and once it is done, the producer can start writing the data into the topic. Okay, so let's say this producer is writing a data into a topic called SMS. This producer is writing a data into a topic called contacts. Okay, and this producer is writing the data into a topic called SMS. Okay, so I have 1, 2, and 3 producers. All these 3 producers are writing the data into our Kafka server, right? Our Kafka cluster with some topic name. Topic is like this. Okay, and on the other hand, what you have is you have your consumer. You have your consumer. Okay, so this consumer is supposed to read the data from your Kafka server or cluster, is not it? And what does this consumer need? This consumer need IP address of at least one system. Only one system should be okay, and the topic to which it wants, from which it wants the message to read. Okay, so the consumer needs only 2 information: IP address of any of the servers, Bootstrap servers, and the topic from which it wants to read the data. Simple. Okay, and once it is done, it will start fetching the data from the equivalent servers. Okay, so suppose I created a topic called SMS, I created a topic called contacts, right? So if you see this diagram says that you have right now 2 topics, SMS and contacts. Okay, so what will happen is under this machine, okay, under this machine there will be a SMS topic, and as you know, the data is actually stored in partitions, right? And what is a partition? Partition is just grouping of data, logically grouping of data like differently altogether, right? Let us assume that this SMS has 2 partitions. Okay, and let us assume your contacts also has 2 partitions. Okay, so your SMS has 2 partitions, so I'll call it P0. Okay, and I'll call it P1. See here, the topic name is SMS. It has 2 partitions, and what happened was P0 partition is here and P1 partition is here arbitrarily. Okay, so it is not necessary that it will be here altogether. It can be distributed across a lot of servers. Okay, similarly, contacts has 2 partitions, so I'll say contact. I'll call it P11. Okay, for our understanding, and I have contact. I'll call P12. Right? So if you see, SMS has 2 partitions, 1 and 2. Contact has 2 partitions, 1 and 2. Right? So SMS, this and this. Contact, this and this. Done. Now, it is possible that one of this node may fail, probably. Okay, and if that fails, then what will happen here? SMS P0 is here, but SMS P1 is here, and if this fails, then definitely there would be a data loss, is not it? Which is what you don't want. So in order to avoid that, we also have a concept of replication factor. So in order to avoid that, we have a concept of what? Replication factor, which means these partitions can now be replicated to other servers. Okay, so what will happen is, in this node, if you see, I have SMS P0, but I don't have the replica of it. Okay, so what will happen is replica would also be created here. Okay, so I'll create a small box here, and this is the replica of P0, this P0 replica. Okay, now if you see, I have one partition here and I have another replica partition here. Okay, so what will happen, whenever there is one main partition and whenever there is a replica partition, out of this one partition would be called as the leader. One partition would be called as leader. The replicas are called as followers. Okay, so the main partition is called as leader and its replicas are always called as followers. Done. Similarly, if you see contact, I have second partition here and I have first partition here, right? So what will I see? For this we created a replica. Done. For this also you should create a replica, and the replica should not be created here. The replica should be created here. Okay, so SMS P1, so I'll say P1 dash. So this is SMS P1 replica, and this is your leader. The original copy is your leader. The original copy is your leader. Okay, and the duplicate copies are your followers. Okay, all right. Now see here, you have a contact where you have P11 and it is the main, so it would be a leader. Okay, and it should also be synced. It should also have a replica, so the replica can go here somewhere. P11, this is a replica. Similarly, this contact P12 is original copy, so again one more original duplicate copy here. Likewise, the replication would happen. Okay, and as a standard, it is always recommended that you have a replication of at least 3, but not less than that. Okay, and that is the standard replication factor we have been learning since Hadoop, right? So in your Kafka also the things would work very, very similar. Okay, now all this P0, P1, all these things, partitions, right, are actually what it looks like an array, is not it? It looks like an array. Okay, and they are actually your data storage. Okay, so remember one thing, that we always write the data to a topic, but it does not matter. And to be very honest, it is not the topic who stores the data, right? It is actually the partition who stores the data, right? And can I say that a topic is basically a collection of partitions? Yes, of course, right? So whenever I create a topic, that means internally there would be a partitions. It could be only one partition, it could be 5 partitions, it could be 10 partitions, whatever it is. Okay, so the data would be stored here. Okay, now let us assume the producer is producing the data, and when it produced the data, it started writing the data into the partitions, right? So when it starts writing the data into SMS partition, what will happen is the data would go and sit here. Okay, the data would go and sit here, the data would go and sit here, the data would go and sit here, like this. The data would be written. As the data would be written, Kafka automatically assigns a unique number, integer, and we call it offset to each of these messages. So whenever you're sending a message, along with the message, the offset number is also set. Okay, so you have offset and message. You can treat this as your key value pair in your Hadoop default text input format, right? So likewise, offset and message would be stored like this. Okay, now since this is the main leader, as the data is written here, the data would also be synchronized into its copy, right? So see, this is a P0 original copy, I would say partition, and we know that we have a replication factor. So because of this replica, you will also see this P0 replicated here, right? And what will happen is whatever you are writing here would also be written here, at the background, and we call this process sync process. Right, the data is getting synchronized. So the data, whatever you're writing on the actual partition, is also getting written into its follower partition. The one is called as leader, the others are called as follower partitions. Okay, now this is very important for you to understand that all these partitions are immutable, which means when you start writing the data whatever you have written in the partitions cannot be changed no matter what. Okay, the data comes and set, and you cannot change it. Okay, so all these partitions are immutable. You cannot change the data, of course, right? So the data keeps coming here, it will be written here, it will also go and be written here, and so on. Now if I have replication factor equal to 4, for example, okay, and if you're using a large cluster, say you have a cluster of, say 100 brokers, right? Now, what will happen is each partisans would be replicated in 4 different places, and it's the leader who actually receives the request, not the followers. Okay, so this is very important for you to understand. The producer, whenever it is writing the data into your Kafka, the data would be always written in the leader and not in the follower. The follower is always supposed to be syncing the data with the leader anytime. Okay, very, very important point. The data would always go and would be taken care by the leader partition. It will store it within itself first, and then it will start emitting it to the followers, and the follower would just keep the updated data in its partition as well. Okay, what the advantage of this? The advantage of this is, if at all this machine is gone, I don't really care, because I already have the replica somewhere else, right? And I can definitely start serving it from that place. Okay, now one thing I want you to understand, see, let us assume when we started this server and we started creating the topic and partitions and all, and we started writing the data into it. Let's say this is the leader partition, this is the leader partition, and after some time what happened was this machine went down. Okay, the machine at which we have a leader partition went down. So what will happen, again, one of this replica partition, out of this, one would be elected as an interim leader. Interim means temporary. Okay, interim leader. So they would be like elected as an interim leader, and then the data, they would be taking care of the entire data processing and all, right? So the data would come to it, it will store, and it will again give it to the replicas. Later, if somehow this machine is back to life, then what will happen? This guy, this P0 partition would again get back the leadership. Okay, so this is very important for you to understand, that if a server is down, if a system is down, then we don't lose that data, because we have already replicated it, and somebody else would become a temporary leader. Okay, and it would continue its leadership until and unless the other node is up, right? Once the node that went down comes back to the life, your P0 partition, the actual leader, would get back its power and will start again syncing the data and start serving the data for you. So this is very, very important for you to understand. Okay, so we understood that the producers are producing the data, right? They are writing the data into a topic, and then that's how the data would be written in the topic. And one thing to understand is, if I have a partition, let's see, if I have a topic called SMS with 3 topics, with 3 partitions. Okay, I have a topic called SMS with 3 partitions, P0, P1, P2. It is not necessary that all these 3 partitions would stay on the same machine. Not really. Okay, P0 may be present in one machine, P1 may be present in another machine, P2 might be present in another machine. Think of it as a block, right? Think of it as a block where each block is present in different machines, and then they are replicated, right? When you say replication equal to 3, then P0, total 3 copies would be available. Actual copy, and then the 2 duplicate copies, right? Again, P1, original one, and then the duplicate copies. Again, P2, original one, and then the duplicate copies. Okay. Now the data would always come and would be written like this: 1, 2, 3, 4, 5, and so on, in this order. Here also in this order. Here also in this order. Okay. So when the data is getting written, okay, remember one thing: within each partition, the data would always be written in ascending order of timestamp, which means this is the oldest data and this is the latest data. Okay. If you are given a partition, you can confidently say that my recent data is here and my oldest data is here. Okay, and that guarantee that ordering would be guaranteed by your Kafka. Okay, as the message arrives, it will be written into this array. Is not it? And that's how your Kafka can guarantee you the order. Okay, however, the orders are guaranteed like this. Okay. Again, in this partition, the message would be written first here, and then here, and then here, and then here. Similarly, in this partition P2, the data would be written here, 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 and then here. Okay. So the orders are always guaranteed. The orders are always guaranteed. However, you cannot guarantee the order within all these three partitions together. Okay. You cannot say first this P0 would be filled up, then only P1, and then only P2. No, that's absolutely wrong. As the data arrives, some data would be written here, some data would be written here, some data would be written here, again some data would be written here, some data would be written here, some data would be written here, and that would be done in a round robinson fashion. Okay. As the data comes, it will start writing the data in all these partitions, just to make sure that the load is balanced equally as much as possible. That's very important point for you to understand. Okay. So it will never, it never, like, guarantees you the order. If you look into P0, P1, P2, you cannot say that my P0 contains only the old data and my P2 contains only the recent data. That never happens. Okay. So you have to understand that point. Okay. Now, whenever you are writing the data to a Kafka, okay, remember, you can always write the data in a key value pair format. Okay, where your value is the original message and key can be used to choose the partition number. Okay, internally some hashing would happen on the key, and based on that the partitions can be done. For example, suppose I have 30 states in India, let's assume. Okay, suppose I have 30 states in India, let's assume, and what I did is the key I chose as the state name. Okay, I choose as state name. So if I choose state name as my key and the message can be anything, then there is always a guarantee that all the Odisha data would always go to the same partition because of the key. Okay, there is always a guarantee that all the Andhra Pradesh data would go to some partition. There is always a guarantee that all the data from Bihar would go to the single partition, and that's how you can basically control your message in the partition. We'll do that practically and we'll see that how it happens. Okay, don't worry about this. So that's how your data would be actually written. You can have a control on your partitions. You can say, I want all my Odisha data to be together because I want them to be stored in a together so that the consumer can consume them smoothly without having to go to the other partitions and so on. Let's talk about this consumer now. Now I have two topics, right? And the consumer needs only your IP address of the Bootstrap servers and then the topic name from which it should consume the data. Okay. Now, as we have discussed earlier, it is possible. It is possible that, I have two producers for SMS. That means my SMS topic would probably get a lot of data produced by these producers. Okay. It is possible that you can say, hey, I want these two consumer to form a consumer group. Okay. Since I created a consumer group for these two consumer, we will do that practically using our Java code and we'll see how easily you can do this. Okay. So since I created a consumer group using two consumers, what will happen is these two consumer collectively would consume SMS. Okay, these two consumer would collectively consume SMS. So now if you see for SMS, let's say we have created two partitions. Okay, if you have created two partitions, then what will happen? Probably this guy would consume partition 0 and this guy would consume partition 1. Probably. Okay, if my SMS has three partitions, then probably P0 would be consumed by this, P1 would be consumed by this, and probably P2 would be consumed by this. Okay, so one single consumer can consume multiple partitions, of course. Okay, but it will never happen that a single partition, half of the data is consumed by consumer 1 and half of the data is consumed by consumer 2. That will never ever happen. Okay, so please make sure that you don't make a mistake here. it is possible that a single consumer can consume all the partisans probably, right? See, if you have created SMS with 2 partisans, nobody is forcing you to create 2 consumers. You can say I want to use only one consumer to consume my entire data. That's absolutely fine. Okay. When would you need this consumer group? When you feel that I'm consuming the data relatively slow and I have a lot of compute engine, and what I want to do is let me create a lot of consumers, put them together in a group. Think about this. I have 30 states, so probably 30 partisans, right? I created 30 partisans, and let us assume the best case, every partisan is storing only one state data. Okay. Now in that case, you may be interested to create 30 different consumers, right? You may say I want to have 30 different consumers so that my data processing would be parallel as much as possible. Okay. Or else you may say I don't care about that, let me have only one consumer and let that consumer consume all the data from all the partisans one by one. That is also possible. Okay. So if you look into this example, this consumer group has 2 consumers, and it may say, okay, the first consumer will consume P0 and then the second consumer will consume P1. You may ask me a question, what if I have 3 partisans? Sorry, I have 2 partisans here. What if I have 2 partisans for this SMS, but I created 3 consumers here? It is possible, right? So I created 3 consumers and I said my 3 consumers would collectively consume SMS data, wherein the SMS has only 2 partisans. In that case, what will happen? The third consumer will not do anything. The reason is because it is not possible to share the same partition. Single partition will not be consumed by 2 different consumers. It will not say, okay, I'll do half and you do 50%. It will not do that. Okay. So what will happen in that case is this consumer 3 would not work. It will just say it's a Diwali day and I'll take off. Okay. So these guys would basically work. Okay. Now look into this. It is possible that you can have another consumer. Okay. And this is not a part of this consumer group. It is a part of its own consumer group. Okay. And this guy can still consume my SMS data as well as my contacts data. Okay. So what I'm saying is there is no restriction that one consumer cannot consume a particular topic. You can have hundreds of different consumers. All these 100 different consumers might want to process the same topic, possible. Okay. But if you put them in a consumer group, then the story is different. If you put them in a consumer group, then they are meant to consume the data from a specific topic, and all these consumers would take up one or other partisans, and no two consumers would be reading the same partition. Okay, so understand this. This is very, very important to understand. Okay, so at a very high level, I would say this is the architecture of your Kafka. Right now, one more thing I want to tell you here. As the consumer is consuming the data, it always keeps track of the offset that it has read last time, because that's how it will be able to identify. Okay. Now earlier we used to see, you need also a zookeeper. We'll talk about that in the coming days. Okay. But whenever you are installing Kafka in any system, you need to have a zookeeper also up and running. Okay. So in the previous version of Kafka, what they used to do was it was automatically written into the zookeeper, what? The offset. Okay. As the consumer is consuming the data, it used to keep a track of all these informations in the zookeeper. Okay, saying that, hey zookeeper, I have read till this point. Okay, and why it was doing that? It was doing that because in case this consumer crashes for any bad reason, okay, then if we bring up another consumer, the other consumer can start working, start reading the data, right? And it can start reading the data from the place where it left last time. Okay, only in case of failure, right? So in that case, this design was required. But in the recent version, what these guys have done, the Kafka team has done, the consumer, as it starts reading the data, it keeps a track of offset, whatever you have read so far, and it writes those information in a separate topic. Okay, so in a separate topic, I think the name was something like this, topic underscore offset. I'll tell you about that. So there is a separate topic, a dedicated topic, which would be used by the consumer internally to keep a track of what are the data I have consumed from a given partition. And anytime that consumer fails, the other consumer might might replace it, okay, and it can know the details of what was already processed by looking into this topic. Okay, that is something very, very important for you to understand. Okay, so I hope you understood the whole architecture. I hope you understood what exactly goes behind the scene, how the partitions and all these things are related together. Let's move on to the document, and we'll go through the document now. All right, look into this diagram, and this diagram says it all. Okay, this is what I want you to understand very thoroughly. See here, producer is a program. Okay, we'll write our own producer. Don't worry, producer is a program, and it is writing a message. See, message for a/0, that means partition 0. Okay, again message for a/1, partition 1. So what it means is, I have a producer who is going to write the data. Okay, and what is the topic names here? This is the topic name A and A. So there is a topic called topic A. Okay, so for this topic we have two partitions here. Topic A, partition 0, topic A, partition 1, two partitions. Okay, for the same topic. While creating the topic, you can write a command which can help you to specify how many partitions you need. We'll see that practically. So topic A, I have two partitions, partition 0, partition 1. Now see here, topic A, partition 0, this was elected as a leader. This was elected as a leader, and topic A, partition 0, this is a follower, right? This is a follower. The first one is a leader, the second one is a follower. Done. Similarly, topic A, partition 1, this is a leader now. See here. So you have a topic A, it has two partitions. Partition 0 is here and partition 1 is here, right? So hence they are elected as a leader. Okay, and this is the replica. Topic A, partition 1, this is your replica, right? So if you see, replicate A by 0, that means replicate for this topic A, partition 0, right? And these two are what? Brokers. These two are two different nodes, two different computers, right? Two different instances wherein your Kafka servers are up and running. So this is your broker 1 and this is your broker 2. And if you see this dash line, that means it is a cluster. It is a cluster of computers. Okay. Now, consumer can read the data from A by 0, that means from topic A, 0, partition 0. And the consumer, the same consumer, one consumer can also read the data from topic A, partition number 1. Okay, and this diagram says it all. Okay, now let's talk about this. Okay, so we are just recapping it again. Broker. What is a broker? A single Kafka server is called as a broker. So in this example, a single node, a single machine who is running the Kafka server process is called as your broker. It's not right. So a single Kafka server is a broker. Now see here, a broker receives message from producer. So this broker would receive the message from the producer. Now let's talk with respect to this diagram. Okay, so I have a topic A and I have a partition 0 here, and this guy is the leader, right? The top one, this guy is a leader, which means if the message for A for 0 partition is sent, it would be taken by this. And that's the reason that if you see the diagram, the arrow mark indicates here. That means for topic A, if I'm writing the data to partition 0, then it would go here and not here. Why? Because this is the leader. It will always go to the leader, right? So it will always go to the leader. Done. So a broker receives message from the producer. So this guy, this broker 1, receives the message from the producer. Done. Assigns offset to them. Now who assigns the offset to any message? It's basically the broker. Okay, because you're sending the data to a broker, the server, and that server is responsible to set an offset to that particular message. Okay, assigns offset to them and commits the message to storage on disk. and that data would be stored on a disk, not on memory. It is persisted on disk. It also services consumer responding to fetch request for partition and responding with the message that have been committed to the disk. So now it is the same broker who would also serve the request of a consumer. The consumer said, I want to read the data from topic A, partition 0, and see here who is serving. This broker 1 is serving. Why? Because it is the leader for partition 0. Okay, hope this diagram is very, very clear. Okay, depending on the specific hardware and its performance characteristics, a single broker can easily handle thousands of partitions and millions of messages per second. That's the beauty of Kafka. Okay, so you can have a lot of partitions, thousands of partitions you can have in a single broker, right? So in a single node you can have thousands of partitions, of course. Okay, and you can send millions of messages per second. Okay, so in a real time you should start with at least 3 brokers. However, in large company you might also have hundreds of different brokers. Okay, next, Kafka brokers are designed to operate as part of a cluster. Within a cluster of broker, one broker would also function as a cluster controller. So which means here in this example, if you see, I have broker 1 and broker 2. Okay, but let us try to say, let's assume this cluster as 5 brokers. Let's assume broker 1, broker 2, broker 3, broker 4, broker 5. We have altogether 5 brokers. Okay, now when you start your Kafka cluster, what happens? See here, Kafka brokers are designed to operate as part of a cluster within a cluster of brokers. So I have 5 brokers. One broker would function as a cluster controller. Out of these 5 brokers, okay, one broker, any one broker would act as a cluster controller, and it is elected automatically from the live member of the cluster. So whenever your cluster is up and running, it will identify, okay, I have 5 brokers, 1, 2, 3, 4, 5. Okay, and it will automatically assign one such broker as a cluster controller. Again, the controller is responsible for administrative operations, including assigning partitions to brokers and monitoring for broker failure. So if I have 5 brokers altogether, out of this 5 broker, one broker would act as a controller and it will take care of monitoring as well. Okay, so that's what this says. Next, a partition is owned by a single broker in a cluster, and that broker is called as the leader of the partition. Let's understand this again. See, partition 0 is actually owned by broker 1 only. Okay, and if you see this broker 2, it is actually holding the replica of partition 0, which means any partition would be primarily be taken care by a single broker only, and that broker becomes the leader of that particular partition, is not it? If you see this diagram, it's very clear. I have topic A, I have partition 0, and this broker 1 is the leader for this partition 0. That is what it means. Okay, a partition may be assigned to multiple brokers, which will result in the partitions being replicated. This line now, right? A partition may be assigned to multiple brokers. Here I have a partition 0, it is assigned to broker 1 as well as it is assigned to broker 2, but the broker 1 has the actual copy and your broker 2 has a duplicate copy or the replica copy, and that's what it says, it is replicated, right? So this provides redundancy of message in the partition such that another broker can take over leadership if there is a broker failure. However, all producers and all consumers and producers operating on their partitions must connect to the leader, right? So this concept of replicating is definitely going to give us redundant data, because the data would be copied, right? The same data would be copied in 2 different places, 3 different places. But the advantage is if the broker 1 is down for any bad reason, then you still have the data in your broker 2, right? Because they are all replicated and so on. Okay, next, the leader of the partition can receive and serve the data for that partition. The other broker would synchronize the data. That's what I said, right? See, This diagram says it all. Producer is producing a message for partition 0 and it went directly to broker 1. It did not go to broker 2. Why? The reason is because the leader for partition 0 is in broker 1, right? And that is what we mean by this term. The leader of the partition, as we know, a partition can be replicated. By default 3 should be what you should choose. Out of these 3, one would be the leader, and that leader is actually going to receive the actual data that should be written and persisted, right? And other guys would be just syncing it, right? That's what it means. The leader of the partition can receive and serve the data for that partition. The other broker would synchronize the data so that each partition will have only one leader and remaining are followers or ISR. So they are the other brokers are also the other partitions are also called as followers, or they are also called as ISR. That means in sync replicas. Okay. So if you look into this example, this guy, the broker 1, topic A partition 0, this is the leader, right? And if you see this broker 2, topic A partition 0, this is actually the follower, or you can also call it ISR. Okay, you can also call it ISR. That means in sync replica. Okay, and it is possible that few partitions are not in sync because it is ongoing process, right? It might take a little time to sync, and that time it would be called as out of sync replica. Okay, so this is very, very important topic to understand. Okay, so what we were talking about was, if you have a server, right, and these are all servers, okay, and say you have a topic called SMS with 4 partitions, right? So you have SMS P0, P1, P2, P3. So you have SMS topic with 4 partitions. So P0, P1, P2, P3, 4 partitions done. And then you have also said that I want 3 replicas. Right, so what will happen? This P0 is here, they will also be replicated here. They will also be replicated here. Right, done. So say likewise P2, P3, P4, and so on, right? So we'll not talk about all these things. Let's focus only on one such partition. So this P0 is the original copy is here, and I'll call it, let's say node 1, node 2, node 3, and so on. And this is a part of your Kafka server, right? Server. Okay. So this guy would be a leader because it hosts the original copy. One of them would be leader, the others are followers. Okay, followers. And they are called as ISR as well, in sync replica. Okay, and they are also called as ISR, in sync replica. Okay, now let us assume one message has arrived and that was stored here. Let's say 1, 2, 3. Few messages are stored here. Done. Now what should happen is, behind the scene, these messages should also be replicated here. Right? This message should also be replicated here on your followers, right? So if a new message is here, then what will happen? This ISR would be OSR, out of sync replica now at this moment, because I've already received some data and the syncing is taking some time, right? It will not take 5 minutes. It should be quick. But then what I'm trying to tell you is, till the moment this data is not synced completely, we call it OSR, out of sync replica, right? But then the process is going on, and within no time you will see them completely in sync. Okay, so once they are completely in sync, and we again call it ISR. So by default we call it ISR because no matter what, as the data is received on the leader, it would also go and get transmitted to your followers, and that would become synchronized very, very quick. Okay, so let's move on. So that's what we understood, right? Next, if as the data arrives on the partition, the leader partition would store the data and would send it to other ISR for replication. Okay, done. Now let us understand this point. What if the broker is down that had the leader partition? We talked about this, but I want to cover everything, right? I have a broker, I have a server which has a leader partition and it went down. What will happen? Let's see. Okay. In that case, the other sync in partition would become leader. The broker that was down, if it comes back later, then it would again become the leader partition. Okay. So the moment the leader partition system goes down, we already have a replica, and out of this replicated data would become the leader partition. Okay. And later on, whenever that system which was actually hosting the leader partition, if that comes back to the live, then it would be again become the leader partition. Now note, the follower partition can be of two types, either sync in follower or out of sync follower. That is what we talked about, right? Because it will take little time. It may not take 5 minutes, but it will take milliseconds, little time to become in sync, right? So till that time it is called as out of sync follower, and once it exactly gets the data, updated data, it again becomes a sync in followers. Next, if the leader partition is not available and if we have sync in follower, then that follower would become interim leader. It's very simple, right? So I have a main partition, I have a broker wherein I had a leader partition and that went down. Now the Kafka server will look into the replica, okay, and it will try to identify, do I have a replica in sync, because it will automatically know it. Okay, if it is in sync, then no harm, it will make it a leader, right? So it will make the other partition as the leader partition, the replicated copy. Okay, but if we have out of sync follower, then we have two choices. Suppose you have the main follower partition wherein the data is coming and getting stored, and now it is slowly syncing with the other servers, other brokers, and at that time the sync was not complete. Okay, the sync was not complete, and at that time what happened, the broker went down immediately and the syncing was not completed at all. It is possible, is not it? Now if that happens, then we have two choices. Okay, number one, wait for the syncing partition to come back, because that guy knows what is the actual state. So we have to wait till the partition is coming back. When I say we have to wait, that means we need to do some troubleshooting to see why it went down and fix it up and make it back, bring it back to the light, but it may take a little time, right? But then your partition would become unavailable till then, because you want to serve the data. The data would be always served by what? By the active partition, the leader partition. And if your leader partition is down, and if you feel that the syncing was not done properly, then you will have to wait till your leader partition is back, because it contains the recent data, right? So in that case, what will happen is your partition would become unavailable and you will not be able to serve the data. That's one thing. The other thing is, you can also do something like this. You can say, I want to make the out of sync in partition as interim partition leader. You may say, okay, I don't have much time. That's okay. Whatever I've lost, I'll see that later. But right now, what I want to do is, let me go ahead with the out of sync data, because at least it has something to serve. Okay. But then the problem would be your data consistency is at stake, because you cannot guarantee that the data which you are giving to the consumer is the recent data, right? Because the recent data might not be present there. Okay. However, this is a very rare case, because the clusters are very expensive, and then they are monitored so frequently, the backup would happen seamlessly and you would not see this kind of problem most of the times. Okay, but if you get to see this problem, then it is basically the admin who should basically get into this. Okay, next, in order to make sure that all partition replication has sync in data, you must set the below parameter for that particular topic. So there are some configuration which you can do. We will look into that in the practical part. However, one such configuration would be minimum in sync replica equal to 2. This ensures that at least 2 replicas should be in sync anytime, no matter what. Okay. Now, if you wish to enable this setting for all the topic in the cluster, then you should set up this at the cluster level. You can set this at the topic level. You can also set this at the cluster level. If you set this at the topic level, then what will happen? For that given topic, for any partitions, at least 2 replica would be always in sync, because the number given here is 2. Okay. Now, you must set default replication factor to 3 so that at least so that you can at least set 2 replicas in sync. As I said, the industry standard is try to have a replication factor of 3 and try to say out of these 3 I want at least 2 to be completely in sync so that any disaster happens, then the other guy can take care of it. Done. Okay, now let's revisit our concept on topic. We know what is a topic, right? But then I want you to understand this through the notes as well. Okay, so let's talk about this topic. So messages in Kafka are categorized into topics. We know this, right? So messages in Kafka are categorized into topics. Topic is basically a tag which classifies the data of a particular type. As I said, if you want to classify my mobile data, then you would basically say my mobile might have SMS data and the call data, the contact data, right? And the applications data and so on, right? So for context, the topic name could be contact. For call, the topic name could be calls, right? Again, you can classify. Incoming call, you may say another topic, you may create a separate tag called incoming underscore call. For outgoing call, you can say outgoing underscore call. For voice message, you can say voice underscore message, something like that. Again, now each topic is broken down into partition. We know it. Messages are written in the partition in append only mode. That means immutable. You cannot edit it. Okay, and can be read in order from beginning to end. So think it like your stack data structure, wherein, or you can say you can assume it like a queue, right? So in queue, what happens? Not stack, sorry. Think it as a queue wherein you store the data in one end, right? And you receive the data from the other end. So you start writing the data like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And when you are consuming, you'll always start consuming from the first 1, then 2, and then 3, and then 4, and so on, right? Okay. Since topic will have multiple partition, there is no guarantee that the message will be in timely order across entire topic. However, within each partition, the message will be in a timely order. We all also discussed this, right? So if you have only one partition for a given topic, then all the data would be in a timely order. The data that comes first would be stored at the beginning. The data that comes at the end would stay at the end. However, if there are multiple partitions, let's say for 1, 2, 3, 4, 4 partitions, then you cannot really guarantee the order, right? But within each partition, there would be always a guarantee of the order. We've also discussed this. Okay. The data would be retained in the partition only for certain time, and it defaults to 1 week. The data written in partitions cannot be changed. It is immutable. We know this. Okay. Now look into this example, right? I have a topic with a name. Any name can be given. Let's say topic name was the topic name. And we have some partitions here, P0, P1, P2, P3, right? And what happened was the data started writing. See here, the data would be always written at the end, appended. The data would be always written at the end, and it will not be written in the middle. Okay, so you cannot really write the data anywhere. The data would always be written on one end, right? And if you see the numbers, these numbers are basically the offset numbers, right? So as per the diagram, the topic is divided into 4 partitions. Look into this diagram. The topic is divided into 4 partitions. Done. In each partition, the data are inserted in the timely manner. All new writes are done at the end of the partition. Each partition can be hosted on different server. We talked about this, right? Each partition can be hosted in different machines. If I have 4 machines, then I may have partition 0 in one machine, partition 1 in another machine, partition 2 in third machine, partition 3 in fourth machine. Okay, which means a single topic can be scaled horizontally across multiple servers where each server is hosting some partition, right? So you can scale it up horizontally, right? So you may have 100 partitions, and each of these partitions are stored in 100 different machines altogether. Next, producer sends data to Kafka broker into a topic, right? So when you are writing a producer code, all you care about is the topic name and of course the Kafka details like the IP address and all, right? So the producer sends the data to Kafka broker into a topic, and the consumer asks the data from a Kafka broker topic. So consumer does not care about the partition number, right? Consumer says, I want to subscribe to a topic called SMS, and let the Kafka broker serve you that data. Okay. Next, Broker collects data from multiple producer and it has to store either producer specific or message specific. So to uniquely identify the message, we have a concept of topic, right? So see, you in a real time, you will have a lot of producers who are producing the data, and all this data would be stored in the server, right? The broker. Now you need to identify the messages, what kind of message it is, right? And that is the reason we have a concept of topic, right? So a topic is basically a tag. As we talked about the example, you when you go to the airport, you are basically given a sticker, right? And that sticker would be pasted on your luggage, and that sticker is basically a tag which says that this bag should fly to Hyderabad, probably, right? So topic is basically a tag which can help us to classify all the similar messages together and nothing more than that. Okay, now it is practically possible that many producers are producing similar data and sending it to various topics, right? For example, I may create a small mobile app and I may install that app in my mobile device, and that mobile device will start sending the data, right, by classifying it. For example, look into this. I have a mobile 1, mobile 2, mobile 3. Three people have their mobile devices. And what we have done is we have started collecting the SMS data, context data, and calls data, right? So I have mobile 1, which is giving me SMS data, contact, and call. I have mobile 2, which is giving me SMS data, contacts, and call. I have mobile 3, which is giving me SMS, contacts, and call. And if you look into this, the data, it would look something like this. I have a producer 1, I have a producer 2, I have a producer 3. The producer 1 might be giving me SMS and contact data. The producer 2 might be giving me contact and calls data. The producer 3 might be giving me only calls data based on the use case, whatever, right? And if you see, all these producers are writing the data into these topics. These are the topics. SMS is a topic, contacts is a topic, call is a topic. Okay. And if you see my consumer side, consumer 1 is consuming the data from SMS as well as contacts. Consumer 2 is consuming the data only from calls. It is also possible that you may have two consumers which is consuming the data from the same topic, right? Possible. But then at the end of the day, they are storing the data are stored in form of what? Partitions, right? And in that case, one consumer is reading the data from one partition, the other consumer is reading the data from another partition. In this diagram, we have not highlighted the concept of partitions, of course. Okay, next, topic replications. We have also discussed about this, but let's understand this. In order to make sure that our data in topic is always available and survive any failure, it is advised to have a topic replicated. A topic must be replicated with number greater than 1, at least more than 1. Give it 2, that's okay. Give it 3, industry standard, but never ever keep it to 1, because that is the biggest risk you are ever taking in your life. Okay, so in the industry standard is 3. This will help us to serve the data to consumer even if a broker is down. If a broker is down, I can always get that data replicated from the other broker, and from the other broker I can fetch those data, and I'll never have a problem of losing the data, of course. Okay, we cannot have more replicas of partitions than we have node in our cluster. So understand this. I have a Kafka cluster and I have a 5 Kafka cluster. Okay, 1, 2, 3, 4, 5. I have 5 cluster. Now if you have a 5 cluster, then your replica should not be more than 5. It can be 5, but it should not go beyond 5. But then I would ask you a question: why would you even replicate it 5 times? It's not really required. You are unnecessarily wasting a lot of memory. Keep it to 3 and the game is over. Okay, so the industry standard is always 3. Now, as we talked about the Kafka architecture, let us try to recap how does it work altogether. Okay, the unit of data in Kafka is called as a message. You know this, right? And think of a message as a complete line or row of a database. For example, if you look into the database, you have one complete row, right? And that complete row is basically a record of, let's say, employee. It's not it. So in Kafka, one complete line is basically called as a message. Okay, so all messages are actually represented as byte array within Kafka. When we do practically, we will see that we will represent them as if they are actually a byte array. Okay, now a message can also have key, which is optional, which is also represented as a byte array. Keys are used when you want the message to be written to a partition in a more controlled way. As I said, if you are dealing with the state of India's data, and let us assume for simplicity there are 30 states in India, then I would suggest you to produce the state name as a key, so that anytime all the data of Odisha would go to the same partition. It should not happen that half of the Odisha data is going to one partition and half of the Odisha data is going to another partition. That will never ever happen. Okay. Now, if key dot has code modulo total number of partitions gives same value for similar key, then all those messages with that key would always be written in the same partition. I'll show you this practically in the program. Okay. So, and this concept is nothing new for us, right? So we have been doing this in Hadoop as well. We know that in Hadoop also we have a concept of partition, right? Which decides the number, which actually decides the reducer number, on which reducer this data should go, right? Very similar to this, right? Whatever key you set, on that hash code would be calculated. You get the hash code modulo total number of reducers, right? So for example, if I say the total number of partitions is 4, then no matter whatever the hash code is written, modulo 4 will either give you 0, 1, 2, 3, right? And based on this number, the partition number will be decided. Okay, we'll look into this in our practical program as well. Okay, next, if the key is not present in the message, then the message would be assigned to the partition in round robin fashion. That is, message 1 may be assigned to broker 1, message 2 might be assigned to broker 2, message 3 might be assigned to broker 3, and so on. And I'm assuming that broker 1 is hosting partition 0, broker 2 is hosting partition 1, and broker 3 is hosting partition 2, and so on, right? So likewise, in the round robinson, the data would be assigned one by one, so that the load balancing is as equal as possible. Okay, and if the key is present, then all the message with the same key goes to the same partition. We know about this. Okay, next, messages are written into Kafka in batches. A batch is just a collection of messages, all of which are being produced to same topic and partition. If the batch size is very small, then the data would be written quickly, but there would be too much of network round trip. See, from a producer point of view, okay, you will produce a lot of data, and the producer can control when do you want to send this data. Do you want to send this data immediately? Yes, send it. Do you want to say, I want to collect 100 records first and then send the data collectively? You can do that. Okay, so this purely can be controlled from your producer side. We will also see that in our practical class, right? So messages are written into Kafka in batches. A batch is just a collection of messages, all of which are being produced to same topic and partition. If the batch size is very small, then the data would be written very quickly. You may say, I want the data to be written immediately, right? So in that case, the batch size would be very small, or maybe even one message, and that would cost you a lot of network round trips. Okay. Similarly, if the batch size is little big, then you don't have to do a lot of network round trip. You may say, let me collect 10,000 records. I'll collect them together and I'll push it up, right? And then it may take a little time for you to collect all these 10,000 records. But then once you have this batch, you just send it to a single in a single request, which means your network round trip would be less in that case. Okay. However, you have delay in writing the data to Kafka. In that case, you will have to face the delay of writing the data to a Kafka. What is the problem with that? No problem, but somewhere the consumer is waiting for your message, right? And if you don't produce the message, if you don't send the message to Kafka, your consumer would not be able to process that immediately. So it's your call. You need to understand how much critical your business is. The batches can also be compressed so that the data transfer and processing can be little fast. That can also be done. You can just add some configuration to have your data compressed before you send it to your Kafka. Okay. It is also possible to have schema associated with the data like JSON, XML. However, they are tightly coupled with the data. So you know that when you deal with JSON data, when you deal with XML data, in case of JSON and XML, you will see the actual data is very small, but then the opening bracket, the closing bracket, or in the JSON, if you see the tag and properties would consume a lot of space, right? So you can also choose something like Avro, in which what happens, Avro says I would not keep my schema as well as the data together. They don't do that. Whereas in case of JSON and XML, if you have seen any XML, what you see is opening tag, some value, closing tag, again opening tag, some value, closing tag, opening tag, some value, closing tag. For every record, you will see like that, right? The biggest problem is more than your data, your metadata is taking a lot of space, right? So for example, employee ID, employee name, employee salary. So these things are taking a lot of space. And Avro says, hey, why do you need to send all this unnecessary junk, right? Every time for each record. So Avro says, give it to me. What I'll do is I'll separate my schema, I'll separate my data completely so that the only the data can travel and the schema can be referred later. Okay, so that can also be done. So you may choose another schema like Avro where the data and the schema are loosely coupled. Okay, next, all the messages that are consumed so far are tracked using offset. Kafka stores this information under a topic called __ consumer _ offset. We talked about this, right? So as I said in the previous version, your Kafka consumer used to write this data in a zookeeper. Okay, saying that hey, till now I have read this offset. But these days, what Kafka has redesigned is Kafka says whatever offset I will consume, I'll write it to a topic called _ consumer _ offset so that you don't have to look into the zookeeper term. Okay, next, fault tolerance are achieved by using replication factor over the topics and partitions are replicated. Kafka uses the concept of leader and follower. We understood this. For every partition, a broker is elected as a leader and leader takes care of all the client interaction. Storing the data, serving the data would be taken care by your leader. It means when the producer wants to send some data, it connects to the leader and the leader starts receiving the data. It is the leader's responsibility to receive the data from producer, store it in a local disk and send an acknowledgement back to the producer. So if the producer is writing the data to a Kafka, the Kafka can give an acknowledgement, okay, saying that, okay, I'm done. I've already received your data and I've written the data to the disk. What kind of acknowledgement can be done? We will see that in our coming classes. Okay, don't worry about this. Okay, next. Similarly, when the consumer wants to read the data, it requests the leader and the leader is responsible to send the data back to the consumer. It's always the leader who will take care of reading and writing the data. Okay, for every partition, we have a leader and the leader would take care of all the request and response. If we have 3 replications for a particular topic, then one of the partition would act as a leader. So see, you have a topic and that topic may have 4 partitions with a replication factor of 3. That means each partition would be replicated in 3 different places, out of which one partition would act as a leader, remaining would act as a follower or sync in replicas. So let's talk about this retention feature in Kafka. Okay, so Kafka brokers are configured with default retention setting for a topic. Whenever you create a topic, okay, you can always configure saying that I want all these messages to be available for, let's say, 7 days or till it reaches the maximum size 1 GB. For example, I may have a topic and I may say I want this topic to have 1 GB of data, and the moment it reaches 1 GB, flush it. Okay, that can also be done. So messages are expired and cleaned off once it reaches the limit. We'll look into that properties, of course. Okay, each individual topic can have different desired setting as per the business requirement. So you can put these settings at a topic level because based on the topic importance, you may be interested to keep the data for longer time as well. So topic can also be configured as log compacted, which means only last message produced within the specific key is preserved. This is useful when you just want the last updated info to be available at any time. Okay, now the question is, why should you use Kafka? Okay, why should you use Kafka, right? So the main reason is because you want a queuing system, a distributed queuing system where the data would come, reside for some time, and you have a lot of consumer that can consume the data for you. Okay, think about this. In a big billion day, how many people are actually like requesting for the orders? Many people is not it. And think about this, if you design this system using Kafka, this would be much more better because let all the order be a part of the Kafka and the consumer, the Amazon system, let them consume the data, process the order, payments and everything. And once it is done, it should send a message to the customer saying that yes, we have already done we have already processed your request and your request is on the way. And I'm 200% sure that Amazon might be using Kafka or similar thing to get the things done. You should not feel strange if they are exactly using Kafka. Probably. I did not work with Amazon, but then most likely they might have been using Kafka or similar product, of course. Okay. Now, why should you use Kafka? When you have a multiple producer, your single Kafka setup can manage multiple producer, each producer being sending the data to a certain topic, right? So it is possible in a real time that you may have a multiple producers who are actually producing the data constantly, and you want that data to be stored in some sort of queue. You should use Kafka. Okay. Multiple consumer. So Kafka also allows you to have a multiple consumer. It is also possible to have multiple consumer reading the data from the same topic. If needed, you can create a consumer group where you have many consumers trying to read the data from a topic and topic, such that no two consumer read same data from the single stream. Let's take this example. Think about this. In Amazon, there are few sellers who are top sellers, right? Whose products are always in demand because they sell good items, and probably they sell the item which is required, which are required by the people. It's not it. For example, if I'm staying in Odisha, which is basically, I would say, the climate is very hot, right? And if you try to sell me a sweater, probably I may not buy it, right? You should sell me AC or maybe a cooler, a water cooler, probably, but not even refrigerator, but not the sweater. Okay, not the sweater of Ladakh and all, right? So it depends, right? So think about this. Few topics will have a lot of messages, and you want more than one consumer to read those messages, right? But then you also want to make sure that no two consumer is processing the same order two times, right? And in that case, what you will do, you will create a consumer group, and you may say, hey, I want to create a consumer group, let me assign 5 different consumers. And when you say consumer, these are all Java programs. I'll show you that practically. Okay, then you will be understanding it 200%. Don't worry about this. So consumers are Java code. You can also write it in Scala. Producers are also Java code. You can also write it in Scala. Now, disk-based retention. In case you don't need real-time streaming, you can still have Kafka preserve your data for n days and let them be consumed later. This option can be chosen on topic basis. In such case, even if there is a problem with consumer application, your data will not be lost. Consumer can be stopped and the message would be written in Kafka. Okay, this allows them to restart and pick up processing message where they left off with no data loss. So your Kafka can also be used as a database, but I'm not talking about SQL database. Okay, you can store the data, right? And you can consume it later, but you are not, Kafka is not designed for that. However, you can still do that, right? Kafka is actually a queue. You should treat it as a queue. You should not say, okay, I'll remove my database and then I'll start writing all my data into my Kafka. You should never do that, right? So Kafka is basically a temporary container where you keep the data, let the consumer consume the data, and once the data is consumed, those data should be discarded from your Kafka. That is what the default behavior of Kafka should be. Okay. Next, scalability. You can use a single broker as a development, and as your data grows, you can add 10 to hundreds of brokers completely online without losing your data. That's the beauty of it. Okay. So the automatic load balancing and everything would be taken care by the Kafka itself. Okay. The scalability of Kafka has helped LinkedIn users grow in excess of 1 trillion messages produced as of August 2015 and over a petabytes of data consumed daily. That's the power of your Kafka, right? So when LinkedIn started using this Kafka product, they were able to consume petabytes of data daily. Okay. Now see, one thing I want you guys to understand is all these great frameworks are written in Java, right? Kafka and whatnot, right? Even you say Spark is written in Scala. Scala is a JVM based product. So if you look into all the Apache products, most of them are written in Java. The reason is because they are reliable. Like there's no doubt at all that any Java, any framework you build on Java will survive, and that's the biggest reason why all these great people have written all these topics in Java, right? Or they've designed all this framework in Java, right? So we must understand the importance of Java. It's not like Java is gone, Java is outdated. I've been doing that since 17 years, right? And then I see that still Java is used in one another way. There are a lot of people who are still doing Java development. People are producing new framework. People are writing new tools. Mostly in Java, the reason is because they have already proved they have already proved that they are the best in the market. Okay.